So far we've done substitution reactions, both SN1 and SN2, and now we've done elimination reactions, E1 and E2. There's this concept that molecules are selective. They prefer certain regions when they react. So this nucleophile, for example, when we were looking at E2, prefers, because it's small, it prefers the internal hydrogens to make a more stable Zaitsev product. Whereas a bulky base, like this one, would prefer a terminal hydrogen. So we call that regioselectivity. Regio is such as in region, a region of this molecule that this is selective for or has a preference for. So let's review that. In the elimination section here, there's a problem where we have this particular alkyl halide and it's reacting with this strong base. And we want to explain what the product distribution is. So that means the major product is this terminal alkene, and this minor product is the internal alkene. So first, take a moment and ask yourself, is this SN1, SN2, E1, or E2? Is it elimination or substitution? If you look, we're forming alkenes, so it's definitely elimination. And then in terms of E1 versus E2, we look at the base. And this base is a strong base, so that means we're going to have E2. All right, now think back to the E2 mechanism. That's where the beta hydrogens were taken by the base, and then the elimination all happened in one step. Now we have multiple beta hydrogens, and if you look at the major product, which beta hydrogens are the ones that were eliminated? You'll see that it was these here, or these, okay? So they're going to give the same alkene. So that means that our base came in preferentially over here, and then did this. So we get our Hoffman product as our major product. Why is there a preference for this terminal hydrogen? So the answer is that if you look at the base's structure, it's a very bulky base. So we've got tert butoxide like this, and this is grabbing the H because of all the steric hindrance from this part and this part of the molecule. So it'll prefer to come in and take a hydrogen. So that's due to steric hindrance. So I'll put a note here, steric hindrance slows a base from taking the internal hydrogens, which would have to be here, okay? Right, so this is called regioselectivity because the base is bulky, so it prefers this hydrogen or this region of the molecule as opposed to this region here. Now there's something called stereospecificity, and that has to do with starting with a certain stereoisomer, you'll get a certain product distribution of stereoisomers. Now here, it doesn't necessarily mean this reaction is always going to give you E or always going to give you Z. It depends on what you're starting with. So let's take a look at what's happening here. Again, we're looking at elimination because I'm making alkenes and I have a strong base. So this is an E2 elimination. And think back to what beta hydrogens were removed in order to make these alkenes. Let's draw them in. Okay guys, so I have these purple hydrogens and the red hydrogen. The red one was taken to make this major alkene, and the minor alkene is from the purple hydrogens. Now if we take a look, we have two possible alkenes we could form here. We've got the same side isomer here, this is the Z isomer, and then we've got the other version which is the E isomer, so opposite sides here. Now, if we look at this carbon skeleton, you'll actually notice that it looks like this one. So it looks like this. And so you would think that if you remove the hydrogen, you should have this alkene. This is the E isomer. But no, what's actually happening is this methyl here is being shown pointed up. So this appears to have some type of a bond rotation, and then the double bond forms. It's not that you get both. You don't get this isomer in very big quantities. So let's look at the reason behind that. All right, what I have here is a Newman projection. Let's place my eye right here. So I'm looking down this bond right here, and I see a methyl group pointing down toward my chin. I see a bromine off to my right, and the hydrogen behind it to my left. So this is what I'm seeing. And behind that is an ethyl group sticking up, and I've got my hydrogen on the left, and I've got this methyl group on the right. Okay, so if we take a look at the orientation, I would say that we would have to have elimination occurring like this. So the ethoxide group would be attacking the hydrogen here, and then we would have the alkene form and the bromine come out. Now what actually happens is we saw bond rotation occur first to get the methyl group up here. So let's show a Newman for that. So I'm just going to rotate this bond in the front so that my bromine is out here. That brings my hydrogen down here, and the methyl group that I'm looking at is right here. And then I'm going to follow that to the carbon behind that, which is going to be the same. I'm just holding that constant. And now you can see that I have less steric hindrance, but also something else that's very special is happening. If you think about these bonds as orbitals, you see that there's alignment of the orbitals when they're in a linear fashion. So first they've got to be planar, but it also helps that they're anti to each other. And that helps the electrons flow. So you get broken bonds leading straight into forming bonds, or forming bonds then lead into breaking bonds again. So you're breaking bonds, forming a bond, breaking a bond, and it's all occurring in this very linear fashion where the orbitals are perfectly aligned with each other for that to happen rapidly. We call this geometry where the leaving group is anti to the hydrogen. We call that being antiperiplanar. An antiperiplanar makes for a faster E2 product than a synperiplanar. So what this means for us is that we're going to have either a major product that is E or Z, and then very little of the other isomer. So there's a very strong preference for one stereoisomer over another, and that's what we're calling a stereospecific reaction. So E2 is that way of the 4 reactions we've learned. So you do need to keep that in mind whenever you see an E2 reaction. And also notice that the minor product is not the E isomer, so the Z is formed preferentially because of the orbital alignment, but also you've got antiperiplanar hydrogens out here as well. So one of these hydrogens could be antiperiplanar to the bromine. Let's say it's the one in the back here. Okay, so you're going to get some of those also being antiperiplanar, so they compete with each other. So let's take a look at this reaction, and we have again a base. Let's assume it's a strong base, and let's assume it's a small base, so we have options here. So if we could take an internal hydrogen to make a Zaitsev alkene, we will, but this is E2, and the new concept is that we want hydrogens that are antiperiplanar to the leaving group. Okay, so now we're down here, and the idea is the same. We have let's say this is a strong base like hydroxide, and it's then leading us to believe this is an E2 elimination because E1 happens with weak base. And the new stuff here is that we want the antiperiplanar hydrogens. So let's draw in our beta hydrogens here and look at which ones are antiperiplanar. So here are my hydrogens, and note that the double bond is preferred to form over here. So that means that one of these 2 hydrogens is being removed with great preference. So can you figure out which one it is? Well, this one is on the same side as the chloride because they're both wedged, so that means they're on the same side. We want the opposite side because they are antiperiplanar. So that means I want this hydrogen and this chlorine to come off. So it's going to form this alkene right here. There's the mechanism for E2, and that's how this is going to be my major product. And then it says not observed, or maybe in insignificant quantities to observe. We're not going to remove this because it's much slower compared to removing that one. So our major product in this case is this Hofmann product rather than the Zaitsev product. So another thing to consider is that this is cyclohexane, so we know it exists in chair forms, and I've got these 2 chairs here. And we want to compare and see that there's the axial form and there's the equatorial form. And let's say this is the beta hydrogen that's getting removed. Well, if you draw the Newman projection, even though we know the equatorial form is more stable, you'll see that that form is less desired for the E2 reaction because the hydrogen is not antiperiplanar to the chlorine leaving group. So in order for it to be antiperiplanar, they have to be diaxial with each other. So the axial form will eliminate faster because of the orbital alignment that we get here. So that's a concept that you'll see in this practice problem. So go ahead and give this a try. I want you to draw these both in their chair form and see in their most stable chair form which is likely to undergo E2 more rapidly. All right, so I think you guys will see when they're cis to each other, we have the tert-butyl group definitely needing to be equatorial. So this is the most common conformer of this molecule. That puts chloride in an equatorial position as well because they're cis to each other. And then over here, I have the equatorial tert-butyl group, but now chloride can be trans and can be on the opposite side or axial. And in fact, that's what we want because the axial hydrogens nearby, my beta hydrogens, are going to be ideal for the orbital alignment needed. So these are both going to be aligned much better for quicker E2. So this will react more rapidly and you'll get a mixture of these two alkene products. All right, predict the major and minor product for each of these E2 reactions. Let's do the first one together. The key is looking at the beta hydrogens, and this is a small base. It's a strong base, which is E2, and it's small, so it's going to prefer to make Zaitsev product if possible. So what I need is to look at the beta hydrogens. So I'm going to put those in here. Now the ideal one is this one. But notice that these are on the same side. So what I would want to do is, if it's possible, rotate the bond and then do the elimination. That will create the Cl on the opposite side, and then we'll have an antiperiplanar arrangement. And that's allowed because of rotation, because these are single bonds. So first let me show the rotation. The rotation puts the Cl in the back, and then we have the elimination from the ethoxide coming in and displacing. So notice my double bond is now here, and instead of getting this Z isomer, I get the E isomer here. So that's my major product. Go ahead and try that, and keep in mind when you can't have rotation because you have a ring, that means you just have to get whoever is antiperiplanar. So give that a try and let's check our answers. Okay guys, with this one I have a small strong base, so this is E2, and I'm going to grab the antiperiplanar hydrogen. Now there's two of them, but I'm going to want the one that leads to more stable product if that's possible. So this one will be slightly faster. Now notice this is no longer wedged because this is now sp2 planar. Okay, so that's our major product there. For this next one, again, I want to choose antiperiplanar hydrogen. So I'm going to choose that one. And the rings, when they rotate, cis and trans stay cis and trans, right? So that doesn't allow me to change which hydrogen I can take. So I'm sort of stuck with whichever one is antiperiplanar, since rotation doesn't change the cis-trans orientation. It does change the up and down or axial equatorial though. Okay, so here we go. We've got the double bond here now, so that's also Zaitsev, rather than having this one though and having the wedged isopropyl group. So that's an important point. And then on this last one, you've got the beta hydrogens on this methyl group versus the beta hydrogens here. Since it's a small base, we're going to go for the Zaitsev. So any of these four would be fine. And we want the antiperiplanar ones. So two of those four will be antiperiplanar. So you just pick one of those. And you're going to get this product. So don't forget about antiperiplanar.